Morning, everybody. How's it sound? Is it okay? The organizers asked me to set the stage for this meeting, whose topic is, what did he say, edgy? So that was a little perplexing. How can I set the stage for a meeting like this? But then I remembered that today, almost to the day, not quite, is the 10th anniversary of Kepler's first light. And Kepler was recently turned off. So I'm going to start my story there. Let's see. Okay, I've got it down here. I don't have a screen behind me, so I have to readjust my thinking here. Lava worlds to living worlds. How a NASA mission sparked the search for life beyond the solar system, because we're talking about exoplanets. I really do, in this retrospective, looking back on the history of Kepler, and I've been working on it now for, well, it's been 20 years of my career, basically. I do think that Kepler sparked the search for life beyond the solar system in a very tangible way. So I named the talk From Lava Worlds to Living Worlds. Lava Worlds is a dream realized. Living Worlds is a dream to be realized. And I think that's why we're here. So I start here with Kepler's first light image. This is the milestone that was taken about 10 years to the day. I think this week, 10 years ago, was Kepler's first light image. As you know, Kepler looked at the Cygnus part of the sky for 4 years, and then when it went into its extended mission, it actually switched and started looking along the ecliptic, in part because we had to, but also because it was really good science. And that basically doubled the lifetime of NASA's Kepler mission. So it flew for almost 10 years, or about 9 years, but eventually we got the empty signal. It did lose fuel and had a finite amount of consumables on board. And so in October of last year, we started seeing headlines like this, you know, RIP Kepler, the little spacecraft that could. So long, Kepler, and thanks for all the planets. And so we didn't have a gas gauge on board the spacecraft, but we did notice that the pressure in the fuel tank was dropping precipitously. The engineers were constantly modeling it and giving us updates. They were also constantly trying to find new ways to write software and to operate the spacecraft in order to conserve those consumables so that we could double the lifetime of the mission. But last year, on November 15th, it was deemed done. And coincidentally, it turns out that that was, to the day, the anniversary of the death of Johannes Kepler himself. So Johannes wrote his own epitaph, which reads, "I used to measure the heavens, now I measure the shadows of Earth." And so it was only appropriate that Kepler, the spacecraft's epitaph, would read, "I used to measure the shadows of Earth's," plural. My colleague Doug Caldwell, the instrument scientist, captured on his cell phone the ops log as they issued the Goodnight sequence on board the spacecraft that day. So this sequence of commands is called the Goodnight sequence, and you see entries like this. Mom has given the go. Mom stands for Mission Operations Manager. The Goodnight sequence command has started. The flight director is calling it. We believe the Goodnight sequence has made it in. And finally, the last one, so long, Kepler, and thanks for all the fish. But just for fun, I wanted to share with you a little story. It turns out that the Goodnight sequence was not a coincidence. It was actually named such, taking inspiration from the movie Interstellar. There's a great scene in the movie Interstellar where the flight director from Earth is wishing them well on their journey, and he recites a poem that has now been made quite famous by Dylan Thomas. And so here I have a clip from the movie Interstellar for you to see. You can go ahead and play.
Do not go gentle into that good night. Old age should burn and rave at close of day. Rage, rage against the dying of the light. Though wise men at their end know dark is right, because their words had forked no lightning, they do not go gentle into that good night. Rage, rage against the dying of the light.
panspermia of sorts, right? Okay, so rage, it did. This is Kepler by the numbers. Over its 9.6 years in space, it observed over 500,000 stars. Confirmed, I think the count is now up to about 2,800 planets orbiting other stars, with another 2,000 or so that are still awaiting confirmation. Detected other astrophysics or discovered other astrophysical results, 61 supernovae. It observed objects in the solar system, new classes of variable stars, and the list goes on, the contributions to astroseismology, et cetera. And all of that with just 678 gigabytes of data, and perhaps most impressively, only 3 gallons of fuel. So I wanted to start by just giving you a few of the highlights with regards to the exoplanet science, these potential cradles of life, right? One of the ways that we will search for life is through remote detection of atmospheric biosignatures in the atmospheres of these planets. So let me give you some of the highlights of Kepler results. 1, exoplanet diversity. The takeaway here is that the diversity of planets in our galaxy far exceeds the diversity of planets in our own solar system. These are thumbnails of artist representations of various exoplanets that were confirmed by Kepler. From the upper left going to the right, we've got planets orbiting dead stars, white dwarfs, for example. Then the next thumbnail shows the lava worlds that inspired the title of this talk, a new class of planets, of rocky planets that are orbiting 10 to 30 times closer to their parent star than Mercury is to our own sun, whose star-facing side is hotter than the temperature required to melt iron at standard temperature and pressure. So these worlds have oceans, but they're not oceans of liquid water, they're oceans of molten rock. The next thumbnail over says, well, if you take that to even more of an extreme, you can see these rocky planets photo-evaporating before your eyes. And we see this by way of the shape of the transit event. The dimming of light that happens when the planet eclipses its star is not perfectly symmetric. You get these really long rise times due to the tail of material. And the reason I'm bringing them up is because this gives us a laboratory of sorts for directly measuring the composition of planets, if we can understand through laboratory measurements what kinds of elements and features, atomic features, molecular features we're looking for in the spectra. Down at the bottom, the blue planet is meant to represent the ocean and water worlds, which are just this very vague term that we're loosely using to describe things, planets that are small but have a very low density, suggestive of a hydrogen and helium-rich envelope, but not an envelope of the size of our ice and gas giants. We don't really understand their physics very well, and I'll talk more about them in a second. The next one, of course, are the circumbinary planets, planets that are present in multi-star systems. And the takeaway there is that the dynamics of these architectures is now has data points anchored to it. Now we can really test the stability models and understand how these architectures are put together. And it really opens up the parameter space for where life might lurk, because we didn't think that planets could exist in these gravitationally complex systems, but they do. And then finally, the last thumbnail represents planets orbiting stars in open clusters. These are gravitationally bound units of stars, and I'm using that as a placeholder to remind myself that there are planets known, confirmed, that are the age of the galaxy itself. That is, when the galaxy was forming, we already had enough heavy elements to form rocky planets. But the devil's in the details. The chemical composition, the ratio of alpha elements to other nucleosynthesis elements depend on exactly where they came from, and those subtle details will dictate the kind of convective overturn you have, for example, in a planetary mantle, whether or not you're going to have plate tectonics, for example. So these subtle compositional differences are very important. This is a raw histogram of the discovery space of Kepler for a certain range of orbital periods. And the reason I show this slide is because at this moment in time, the most common planet known to humanity, not necessarily the most common planet out there, but the most common planet known to humanity in our discovery space right now is a kind of planet we do not have in our own solar system. And these are that blue icon I referred to. that we're loosely referring to as like aqua worlds, water worlds, ocean worlds, super Earths, mini Neptunes. There's 1,000 names. None of them fit quite right because we don't understand their diversity. So that's just, we must keep that in mind. If you convert the observed histogram into the intrinsic population of planets in the galaxy, making bias corrections to your survey, corrections for completeness and reliability, you get a histogram that looks like this, where now the y-axis is not the fraction of planets observed, but the average number of planets per star. And so this is a marginalized distribution over radius, or the size of the planet. And what we expected going in, like in the solar system, we expected there to be few large planets and then growing numbers of small objects as you go down to Mercury-sized and even smaller. It would continue to rise. But instead, what we're finding is that the radius distribution is complex. It has valleys. It's not a simple power law. It has a valley that's centered around 1.8 Earth radius, and we need to understand through formation and evolution models exactly how that valley is sculpted, but it's likely sculpted by a combination of formation, evolution, migration, and irradiation processes from the central star. All of those things are corroborating to carve out that valley. Here is another way of looking at it. So Evan Seinikoff recently released his PhD thesis that's based on 47 subjovian mass measurements from K2. And so now you can plot this in a different way. On the y-axis, you can plot density, and on the x-axis, you can plot radius of the planet. And you see through the heat map underneath that these two populations are nicely distinguished. And in between is that valley somewhere around 1.8 to 2 Earth radii. But what I want to also point out here, it's not obvious from this diagram because you can't see error bars, but it's reflected in the heat map, is that even to the left of that valley, there's a spread in density. There seems to be compositional diversity. And so the takeaway message there is that even amongst what we consider to be the terrestrial-sized planets, there might be compositional diversity. And we talk about following the water, finding planets where liquid water could pool on the surface, but a word of warning, too much water might be too much of a good thing. You might end up with too thick of a layer where you don't have reasonable pressures at the interface between the rock and the liquid. Here's another way of looking at the Kepler sample. This is the orbital period on the x-axis versus the radius of the planet. These are all of the discoveries. And in pink and blue are non-Kepler discoveries for comparison. The yellow points are Kepler discoveries, and you see many patterns in this diagram. There's an incredible amount of information in this diagram. The first thing you might notice is that there are no planets in the bottom right-hand corner. That's a sensitivity bias. That's where Kepler even peters out in its sensitivity. But you also notice that there's a lack of planets in a bird beak on the left. And that bird beak is highly statistically significant. It is reflected in occurrence rates. And the slopes of that bird beak are telling us important information about the size of rocky cores that form, about the interaction of the stellar radiation as a planet migrates inward and tries to cross those boundaries. Depending on its surface gravity, it will either shrink in radius because the envelope gets photoevaporated, or it will grow in radius because the surface gravity is so high that it inflates the radius but holds on to it. It doesn't actually photoevaporate. So those slopes will tell us something important about formation and migration processes as well. And of course, we're very interested to know about migration here in these 2 days, talking about panspermia and how life might be transported from one place to another. So speaking of that, Kepler taught us a lot also about planetary architectures, how planetary systems are put together. Because of all the 4,000 planets that Kepler identified, they're actually associated with only 3,000 stars. Many of them are in multi-planet systems. And there are various kinds. I mean, we are very familiar with Trappist I, the Trappist I system, 7 planets, lots of near-mean motion resonances. It looks like these planets migrated in and settled into a very specific configuration. These tidally, or these dynamically compact systems we observe have very, very low mutual inclinations of the planets. The dispersion in the obliquities are very, very low. That seems representative of a very gentle migration process. So I would say that the fact that these systems exist in this finely tuned configuration is evidence for some gentle migration process. However, on the right-hand side, you see another cartoon. Well, in the left figure, right panel, you see another cartoon which shows a different kind of architecture, where we observe a small number of planets, maybe one or two, but doing radial velocity measurements, we find evidence of other additional non-transiting planets in the system at different angles, highly different angles, inclination angles, suggesting that as you go to smaller numbers of transiting planets that are observed, there is more dynamical heat in the system. That's evidence of a more violent migration process. And that's what's being shown in the right panel. There's a beautiful paper by Wei Zhu, who's at Toronto, where he very carefully looked at the inclination and eccentricity distributions of Kepler planets. And by looking at the subtle statistical overview, generalized transit durations, when they're too long, that's evidence that you have an eccentricity and the planet is going slower during the transit geometry. And so by looking at that distribution, you can back out what the eccentricities look like as a population. And what he notes from doing this study is that the fewer planets you have, the more inclination dispersion you see. He also comes to the conclusion that in the multi-planet systems, the average number of planets in periods less than 400 days is 3. And coincidentally, the solar system has 3 in that range as well. So this kind of work hinges on the Kepler sample, which is a statistical sample. But it's very difficult to get mass measurements, eccentricities, and inclinations from the Kepler data alone. We need masses for that. And so that's kind of a segue into the next part of my talk. But before I do that, I will show this image. I have bookends on this first section. The first bookend was Kepler's first light. The last bookend is Kepler's last light, which was taken just a few months ago. Or this was the last full-frame image that was taken before the spacecraft was shut down in November. You can see there's black holes, black spaces where, not black holes. There are spaces where you don't see the detectors because over the years we did lose a couple. So it's like seeing an elderly person with the wrinkles that tell the story of their life. I love this image. Okay, so if we, hello, yes. Here is a spatial diagram. All I've done is I've taken the right ascension of all of the host stars and the distance to that system, and I plotted them in this polar projection. And so what you're seeing here are all of the transiting planets in yellow, and the large spray is the Kepler planets that were discovered in the first 4 years in the Cygnus region, stretching out to something like, 6,000 light years or even farther. What we're really interested in, though, if we want to get good mass measurements and we want to really pin down things like the details of planetary architectures or understand the compositional diversity of planets, both of those things require that we measure things like mass and eccentricity. So to study that, we want the nearest planetary systems. Kepler observed in this cone stretching out 3,000 light years. Of course, it also observed over the ecliptic for 80-day segments. So those segments don't reach quite as far out in orbital period. So primarily, the prime mission search base was out to this 6,000 light years, 0.25% of the sky. As you know, the TESS mission, the Transiting Exoplanet Survey Satellite, launched recently last year, July of last year, and is really doing an all-sky survey to focus on the nearest planetary systems. So if we look at the planetary systems within 100 light years, this is what we have. I've simply zoomed into the central dot of that polar projection plot. There's just a tiny handful of planets there. But TESS is already making good on its promise. It already has over 400 planet candidates identified, and some of them have been confirmed even in this very tight part of parameter space. So the yellow points that you see in the background are the result of more than 2 decades of looking for planets. TESS has added a significant contribution already just through observing a few months of its data. So it is making good on its promise. Now, like I said, we need the masses, and TESS's level 1 science requirement is to get the masses of 50 planets smaller than 4 Earth radius. The UC faculty have formed a unified collaboration to get as much Keck time as possible to get these masses. We've got Courtney Dressing at Berkeley, Paul Robertson at Irvine, Eric Pettigura now at UCLA, Stephen Kane at Riverside. So we put in a large proposal for Keck, and we also collaborated with Caltech in Hawaii, Andrew Howard and Daniel Huber, and submitted 4 large proposals this year to do TESS follow-up. And if we get what we asked for, we hope to have a total of 150 nights and be able to get masses of 100 exoplanets that TESS identifies. It's through that kind of work, of that scope, that we will be able to answer some of the fundamental questions that Kepler has teased, right? Another way to approach this, for example, the issue of compositional diversity, instead of looking at the bulk composition of the planet, to do a top-down approach and look at what's being outgassed, look at their envelopes, look at their atmospheres. So this is the subject of transmission or emission spectroscopy. Here's a cartoon of how that works and the kinds of features you might expect to see. And the tools of the future are going to be the Webb Space Telescope and the 30-meter telescopes that we're building on the ground. Hopefully, within the next 5 to 10 years, we will have 3 30-meter class telescopes in both the northern and the southern hemisphere capable of taking spectra of some of these exoplanets from the ground, and even seeing some in direct imaging and getting the full phase reflected in thermal light. But Webb is going to be launching in 2021, maybe earlier. It's on track for a launch in the first half of 2021. This is what you see. The blue dots in this cartoon are what you would see with Hubble. Hubble has done some transmission spectroscopy, but it's only for a very narrow range of wavelength space using a smaller telescope. Webb is going to have the capability of observing planets from at least 1 to 5 microns, actually out to 10 microns. It's going to cover this part of parameter space and give us not only water features, but also carbon dioxide features, and of course methane as well, and who knows what surprises. However, a word of caution here too. It has been demonstrated through simulations that at least for the small planet population, you cannot reliably retrieve atmospheric properties unless you know the mass a priori. So if you don't have a mass from Keck or from transit timing variations, and you've got a small planet, all bets are off because there is a degeneracy between the surface gravity and the temperature. The scale height is driven by multiple factors. It's going to be driven by the temperature. It's going to be driven by the mean molecular weight of the species. It's going to be driven by the surface gravity. So if you don't know the surface gravity, you're not going to be able to disentangle those degeneracies. Okay, so we are about to embark on a new era of exoplanet exploration, and that is the characterization of exoplanet atmospheres, understanding the diversity of atmospheres. One of the most exciting things I think is going to come out of this is understanding the gray area in between, those exoplanets that we do not have in our own solar system. Webb is going to do a bang-up job understanding those from the perspective of their atmospheres. Okay. Now, all of this work that our community has done over the last couple decades has transformed the landscape. In 2017, Congress added a 10th objective to NASA as an agency. That 10th objective, and this is everything that NASA does, objective number 10 now reads, the search for life's origin, evolution, distribution, and future in the universe. To me, this is a megaphone for the search for life. And that has trickled down into other programmatic changes. I want to first also mention that the National Academy of Sciences did an exoplanets strategy report, science strategy report, And in that report, they called out the need for interdisciplinarity, that the search for life on exoplanets will not be accomplished by a single team of researchers nor by a single method. It will happen only when researchers bring together the combined insights of astrophysics, planetary, earth science, and heliophysics, and provide them the resources to collaborate. And this statement has also led to very specific programmatic changes at NASA headquarters. If you look at the Rose's call, for example, there are now exoplanet science funding pathways both through planetary and through astrophysics. A couple words about astrobiology. Here's some thumbnails just to kind of sort out the pillars of astrobiology. There's been some reorganization at headquarters with regards to astrobiology, and this is the way that they're dividing things out. You've got kind of the origin of life in the upper left, Earth in time, understanding the various faces that Earth has presented to us in time, and the archaeological evidence that goes with it. Exoplanet system science, looking at planetary habitability of exoplanets, but in a multidisciplinary sense. The ocean worlds, and then, of course, the biosignatures. This year, there is going to be, so there will be funding calls for each of these 5 pillars, but they will be on a rolling basis. This year, later this year, you will see an announcement for a funding call for the exoplanet system science, prebiotic chemistry and early Earth, and from early cells to multicellularity. Those are the 3 of those pillars that will be, that we'll see a call for this year. At the end of this talk, I would just like to end by, I've moved. And you know, for me to leave NASA, that's a big deal. Working at NASA was my childhood dream. So I must have had a really good deal, and I did. And it's related to this idea that Kepler has catalyzed the search for life in a very tangible way. And so the best way that I can continue to leave a legacy and continue this search for life in the future is to coordinate the amazing expertise at UC Santa Cruz and get people there that are working in all of these areas of expertise represented by the 5 pillars of astrobiology to focus their efforts on planetary habitability. So just by way of giving my forwarding address, I would like to introduce you to just a couple of characters at Santa Cruz and the work they're doing. We've got Jonathan Fortney and Ruth Murray Clay in the astrophysics department who are doing theoretical studies of planet formation and evolution. Ruth is a dynamicist studying architectures of planetary systems and their evolution. Jonathan is studying evolution and how it affects atmospheres, how those atmospheres are evaporated away. Andy Schemer is our instrumentation guru, but also does exoplanet imaging. Andy is leading the early release science for Webb on the imaging side, and I'm leading the early release science for Webb on the transiting planet side. So we're both there at Santa Cruz, but Andy is also building instruments that will be integral field unit spectrographs for direct imaging and taking spectra of directly imaged planets on Keck, and then that instrument will be able to be ported to the TMT in the future. We have people studying ocean worlds. Here's a picture of Francis Nemo in the Earth and Planetary Science department. He was involved with the study that provided evidence that Pluto is also an ocean world. We've got Z Zhang, who is studying hazes. Hazes are really important for understanding the spectra of exoplanets, especially in transmission. These hazes create scattering and high optical depth. Oftentimes they mask spectral features which preclude us from seeing greenhouse gases, or in the future might preclude us from seeing biosignatures. So it's extremely important that we understand these hazes. We've got David Deemer, who's doing a multitude of things. I think he's here in the audience, and so is David Hostler. David Hostler you will hear from later, so I didn't include his picture. But origin of life work through the biomolecular engineering department with both David Deemer and David Hostler. Talk to David Deemer. He has a lot of interesting things to say about shallow pools, deep ocean, and the timing and how they interface. Miriam Tellis is doing laboratory work in cosmochemistry in the Earth and Planetary Sciences department, but she's partnered with Jonathan Fortney to think about outgassing events on rocky planets. in order to better understand their atmospheres. So she's doing laboratory experiments to understand the composition of those outgassed volatiles using meteorites in the lab. And then finally, I wanted to give mention to Sandra Faber. Sandra Faber is a cosmologist, a rather famous and notable cosmologist at UC Santa Cruz. She's now emeritus. But she's been thinking for a long time about the future of Earth. And she would like to create a future of Earth, or an Earth Futures initiative. And the idea is that no concept of the future is complete unless we think on cosmic timescales. That understanding the sustainability of life here on planet Earth is intricately tied to understanding planetary habitability and where life might exist out in the universe. The two go hand in hand. So when we go out and we search for life in the universe, we're learning something about the sustainability of life right here on planet Earth. But the other thing that I think, and I put 1 million years down at the bottom because that's the time scale, the cosmic time scale that she has in mind, not just with regards to astrophysics, but also with regards to ethics, economies, all of the other very complex questions that we're dealing with today. Who lives, who dies in this Anthropocene? I think that this is very important, and I think that what Santa Cruz is bringing to the table is also an ethics perspective. And so I'm ending this talk with this slide. I was in Denmark last week, and at the art museum, the main art museum in the center of Aarhus, they have a temporary exhibit. And this one, I can't pronounce the artist's name, Z Jade, maybe, I'm not sure. Apologies if I botched that. But this artist has created a map of technological ethics. So it looks like an old map of the world, and what you're seeing here is just a piece of it. The map is gigantic. It's across floor to ceiling, across a huge wall. And every geological feature is labeled with an ethical conundrum that we are facing today. And I sat there and I studied this map quite carefully. And nowhere did I see the kinds of ethical conundrums that I myself am facing. For example, somebody comes to me and says, I think we can make a lot of money for exoplanets, Natalie. I think that we should market it as like the search for Earth 2.0. And what goes through my mind is, well, that's great, except one, it implies colonialism. Two, it implies we've screwed up this world and now we need a backup plan. And I don't think that that's the mentality that we should have. So that's an example of an ethical conundrum. We're about to become an interplanetary species. What are our moral, ethical responsibilities as scientists as we embark on that? Do we have any? Should we even be asking the questions or having the conversation? And the list goes on. But the reason I'm bringing it up here is because 2 days before I was invited to give this talk, not 2 days, a week and 2 days, I was having dinner with Doug Lynn, another famous theoretical exoplanet scientist. Doug Lynn and I were talking. It was the first time I had ever had a serious conversation about panspermia in a way that I had never thought of before. And basically the idea was, if we are really as a human species in dire straits, at what point do we think about preserving this incredible complexity that has arisen here on planet Earth? And should we? I don't know what the answer is to that. It actually quite terrifies me. Right now, I would love for you to prove me wrong. But going into this exercise of these 2 days, first of all, I'm glad we're having the dialogue. Second of all, I think that we need to keep in mind as a scientific community that we need to be talking to the philosophers about the ethics of what we're doing. Thank you very much for having me. Do we have time for questions? Did I speak too long? Okay, good. I think I'm coordinating my own questions. Alex over here, maybe? It's the first one I saw.
So Natalie, great talk, congratulations, and I hope you get the 150 nights of Keck time. But the test stars are so bright that the 2.4 meter automated planet finder at Lick Observatory, which is used every night to take spectra, can of course measure masses as well. Do you plan to mount a giant campaign with that telescope as well?
Absolutely. So everything that's brighter than, I think it was 8th magnitude, we're doing on the APF at Lick, which is an amazing resource. and is currently in an upgrade process to make it even more sensitive. And then everything fainter will be done on Keck.
Great.
Yeah. Yes, in the back there.
Yeah, thanks. Great talk. I'm Greg Matloff. I did some of the early work with Michael Mountner on directed panspermia with near-term technology. It certainly is something we can do, and it certainly is something that has to be debated. You're absolutely correct. You might want to look Michael up. Mike Mountner, he's in New Zealand. He's a biochemist, and I believe he still heads up the International Panspermia Association, something like that. It's Mautner, and might be a good contact. Welcome.
So key takeaway, could but should. Should we? Any other questions? Yes.
Thank you. My name is Jeff Kuhn. I think that these are such important questions, and you make the connection between ethics and what we can learn by looking at exoplanets. It seems that the answer to a lot of these conundrums is to do direct imaging. And I'm frustrated that in fact we haven't made that a huge priority for all of ground-based astronomy, that the exoplanet community doesn't rise up and say, we have to have our own telescope. You made the point that the 3 extremely large telescopes are going to help, but they're neither the right telescope nor will we have a lot of time on them. It seems like this really is the time for this community to make itself heard in a really big way for a dedicated telescope that does just these problems.
You are preaching to the choir, absolutely. I didn't talk about what's on the horizon after TMT, W1st, Webb, but go big or go home. I mean, we're about to initiate a decadal review, Astro 2020, and what's on the table are design studies for direct imaging space-based telescopes to give us the 10 to the minus 10 contrast levels that we need to image an Earth. And I'm very worried because I think that everybody's feeling very nervous. How in this climate, with all the Webb delays, are we going to have the cojones to go ask for a 12, 16 meter class telescope in space? But like I said, I say go big or go home.
Well, actually, it doesn't have to be in space. It can be on the ground. And I think that those arguments are ones that we should look at carefully. We're not going to do 10 to the minus 10, but we're going to do problems that address census of 100 of the nearest exoplanets.
And the 30-meter class telescopes are going to do that, absolutely, right?
I don't think they will. They're not the right telescope, but we should be having that discussion.
We need to develop the right instruments, certainly. But we have on a small number of stars a hope of getting 10 to the minus 6 contrast for potentially habitable planets around M dwarfs on the 30-meter class telescopes. And of course, that means we can detect everything else that's brighter and further away as well.
Natalie, here first.
Yeah. Sorry.
Thank you for a great talk. Kind of philosophical question. Which approach you deem better philosophically? The Kepler approach to look just at a portion of sky in depth, or the TESS approach that looks at the whole sky? Because here we want to study population, here there is possibility of discovering new Earths.
Yeah, they're completely different science objectives. Kepler's science objective was to do a demographic study of exoplanets. So we went deep, one field of view, long stare. We observed for 4 years. Nothing's going to touch that data set in the next few decades, right? Nothing is planning a 4-year stare. TESS, on the other hand, is looking all sky survey for the closest transiting planets. So it's a completely different science objective. TESS is trying to find targets for Webb to study the atmospheres, or for Keck, telescopes like Keck, to get masses so that we can understand compositional diversity, so that we can understand architectures. So they're just completely different. I wouldn't even compare them. Even though they're doing the same method, I wouldn't compare the two.
Yeah, that's why my question was about the philosophy. If you have to choose one of the two, I mean, I know that we want to have both of them. Yeah. Fortunately, we do.
You're asking me to choose between my children. I'm not going to do that.
Up front?
Yeah, David.
Hi, Natalie. The slide that you had adding the 10th area to life, search for life in the universe, both Steve and I noticed that there were some missing disciplines. This is about searching for life, but biology was not mentioned as a discipline, and chemistry was not mentioned as a discipline. So I wonder if that was purposeful, inadvertent, or why those disciplines were absent.
I don't have the answer for you. I have to ask Congress.
Hi, good morning. This is Renee Heller from Göttingen. One of the most interesting systems, at least for me, in terms of panspermia or multiple habitable planets around a given star is the Trappist I system. Do you know what are the odds for JWST to characterize those atmospheres?
There are several papers on the subject. I think we do have a hope for some of them, not the more distant ones, some of the more interior planets. Webb, they're going to try. It's not going to be easy. You know, I think that Webb should do a legacy survey, a very large survey of a set of planets that uniformly sample as best we can, both planet and star properties and maybe dynamical properties like eccentricity. And so I'm working towards that objective. When I'm choosing the planets that we will measure masses of, I'm looking at it from that lens. And when I look at the population of planets that we know so far, Trappist I stands alone in the parameter space quite dramatically. Whether or not TESS will even find another system like that, I don't know. It's such a rare beast. But just to say, to emphasize your point, that it is very valuable, and I do think that we should try. I want to be careful, though. I think the community as a whole is worried that we are going to spend a lot of time integrating on Webb to chase down a marginal signal that we may not even see. Whereas we could take the 200 best planets that uniformly sample all these axes and do a large survey of atmospheric demographics. So we have to figure out the right balance. But there are some papers out there that talk about the sensitivity limits and what's expected. And keep in mind that when they do those calculations, they're assuming a low mean molecular weight atmosphere. That's kind of a best case scenario. So.
Back here.
Thank you for your talk, Natalie. In response to the previous question, in the PI time for the nearest instrument, which includes 204 hours, some of that time will be allocated to observing several of the Trappist I planets, including those in the habitable zone. Yeah. So that time is scheduled.
There are GTO targets, that's correct. Yeah, and Lauren is part of our NASA Keck team, or our Keck UC team. She's our Hawaii representative. So I just wanted to give a shout out to her. Any other questions?
Okay.
Yes.
Thanks. So Natalie, you and I both do science for a living, and that's a privilege, and we are grateful all the time. But I know that you're passionate about this as I am, and that is how do we open up the worlds of science in all the many fields in which citizen scientists could play a role. And the exoplanet area is something that people find tremendously attractive. Certainly people at already existing organizations like astronomical societies and so forth. But it seems to me that there's a lot of work to do on these, and that vetting individual planets, individual detections, and so many areas of exoplanet are just crying for more workforce. And in turn, of course, this would normalize science as a topic of conversation and activity within our nation and hopefully the world. And I wonder what areas of exoplanets you think might be most suitable for the study by people who don't do it for a living.
Yeah, it's a great question. I do feel very strongly about citizen science because I myself didn't decide to pursue science until I was a junior in college and switched my major from business to physics. And the reason I got hooked is because I was able to experience firsthand what it is to do science, right? I think young people don't understand the thrill of discovery, what that means. So providing the public with that opportunity accomplishes many goals. It first tells them what science is, but also it gets them like owning it and understanding it and educating them in the process. So it is very important. I think the exoplanet community has done that very well already. in many different venues. There are multiple citizen science platforms for looking for transits, and there are planets that have been discovered by citizen scientists. I guess that the first thing you have to do is make sure that all of the data is in the public archive. Will the rest just take care of itself? No, probably not. It'll probably require some shepherding from the scientific community. But the good news is that the industry sector is also very interested. You saw planet discovery with collaboration from Google that was inspired by Google machine learning and the like. So there's a lot of room for partnerships, but I'm not sure that we're leveraging them to their full potential. Yeah. Okay, very good. On to the next. Thank you.